Okay, hi everybody, it's Dr. Schultz, and I'm going to give you a quick video lesson this morning, and we're going to talk about learning targets number 7 and number 9. First of all, number 7 says that I can define force and describe common examples of forces, and number 9 says that I can represent the individual forces acting on an object by sketching an appropriately scaled and labeled free body diagram. So let's get started. You'll need to have a look at this green sheet that gave out yesterday in class. This lists the common forces that we're going to run into this semester in mechanics. Okay, it's a pretty big list, and we're just going to do a really quick overview of what these forces are. And I'm just going to take them in small pieces. So we'll take the first two together because they're kind of related. The first force on the list is universal gravitation. The symbol is capital F with a lowercase g for gravity. And this force is basically the force of mass A acting on mass B. In words, you could say that this force is the gravitational pull of any mass A on any other mass B when they are separated by a distance r. Okay? And the direction of these forces is that force A is always directed towards B, and vice versa. And it has a formula that goes with it. So this first formula is actually the first force is what was discovered by Isaac Newton, and he came up with the formula that was used to describe it. We will not use the formula for a little while, but it's important to at least point this out right now. Now, the second force on the list is actually closely related, and that's the force of weight, and we did talk about that yesterday. And the force of the weight is basically the force of an earth acting on an object. This is a special case of the force of gravity, because it's the Earth's gravitational pull on an object when the object is near sea level. Okay? And the direction of this force is always down, which means technically towards the center of the Earth, and we now know that that formula the formula for calculating the weight is equal to mass times g, which is a constant which is equal to 9.8. Okay, so we do know a little bit about weight. There's another group of forces here on your list. There's the applied force, normal, tension, and parallel. These have their own symbols. And in each of these cases, these forces are basically, they're described here. So an applied force, for example, is the force of an external agent on an object. So it means a push or a pull exerted by a person, an animal, a machine, etc. An applied force is kind of a generic label. It includes a lot of things. Its direction is in the direction of the agent's push or pull, and there really isn't a formula for it. The next force on the list is called the normal force. And the normal force is the force of a surface supporting an object. Its direction is always away from the surface at a 90-degree angle, and there's a formula which we may talk about later in the semester, which we won't worry about now. Tension is basically T. It's the force of a rope on an object, and it's a pulling force. It comes from a rope, a cable, or a chain, and the direction is towards the puller. Again, there's no formula for that. And finally, the parallel force is the force, it's the gravitational pull on an object on an incline when it is angled theta degrees above horizontal. So basically, this is the force of gravity that's aiming down a ramp, that's directed down a ramp, or an inclined surface. And it has a formula too, which we'll worry about later. We also have several forces due to friction, and the forces are basically kinetic friction and static friction and air resistance. Kinetic friction is basically the force that resists an object's actual motion when it's sliding across a surface. So the key thing is that the object is actually moving. Static friction is the force that resists your attempt to cause an object to slide across a surface. The object is not moving, but it's trying to. And air resistance is a force of air that pushes back on an object that's falling through the air. It's also called a drag force. And these forces of friction all have specific formulas which we'll meet later on, so we're not going to talk about them really right now. But the interesting thing about friction is notice that friction the frictional forces always have a direction that's opposite the direction of the object's motion or its attempted motion. The last force on the list here is the force due to an ideal spring. It's called a restoring force, and it basically tries to pull an object back to the resting place of the spring, which we call the equilibrium position. And this last formula is very famous in physics. It's called Hooke's law, and we'll be learning about that later in the year. So I think that kind of wraps up kind of going through this list of forces. There's obviously a lot to know. There are a lot more details, which we'll pick up as we go. You know, at this point we know weight pretty well, and the other forces we might just identify them, but we might not know how to deal with them too well. And that's okay. Alright, so what you guys are going to be doing soon is you're going to be drawing some pictures where you represent these forces with arrows. So you'll need to have the free body diagram activity packet out. Okay, so the first page looks like this. And I'm going to just read through the top part of this. It says, in this activity you will draw free body diagrams, or FBDs, for a variety of different objects in different situations. Free body diagrams are used in physics and engineering to identify all forces acting on a particular object. An accurately drawn FBD will reveal whether or not a net force acts on an object. FBDs are the starting point for writing equations that determine the magnitude of the net force on an object in the horizontal and vertical directions. So basically a free body diagram is a sketch. Okay, here are the rules. It says an FBD is drawn for a selected object of interest. Usually in a description, the object of interest is indicated in bold, or it's made pretty clear from the description. Rule number 2 is when you draw force vectors, in other words when you draw the arrows, you want them to begin in the center of the object, usually kind of like the center of mass, and they point outward. Okay? Number 3, you want to use a straight edge to draw your vectors, so make them neat. Number 4, your vector lengths should be drawn to scale, or at least kind of to scale, to show that forces are either the same size or not. And finally, number 5, when you label the vectors, you want to give them labels that might start with a nickname. For example, W stands for weight. But I'd also like you to get in the practice of labeling them in this notation, where you say weight is the force of the Earth on the object. And I kind of challenge you, as you draw free body diagrams, to think about every force as being the result of one object acting on another. Okay, so what does this mean? Let's take an example of a physics book resting on a table. Okay. So here we have a physics book. The table is underneath. We're going to put a dot right in the middle to show kind of the center of mass of that book. So the first thing I want to do is draw arrows representing the forces. Okay, so one arrow I can draw is the force of the table supporting the book. And that's called the normal force, if you remember from our list. And I want to call it normal force in my picture, and I want to also call it F of table on book. I want to give it that label. It's the table supporting the book. And the normal force, of course, pushes up because it's supporting the book, so we draw it that way. Now, the other force that acts on the book is probably the one I should have started with, the more obvious one, which is the weight. And the weight is the force of the Earth pulling on the book. And of course, that's a downwards force. And so you would call it weight, you label it Earth on book, and you draw an arrow that points down. And the idea would be that these two arrows are going to have the same length, but they're just going in opposite directions. So essentially they cancel each other out. Okay, and so we're pretty much done with this free body diagram. It's a very simple one. There's only two forces to draw. So if you go and ask these questions, how many forces act on the object? Clearly just two. Do these forces cancel each other out? Yes, common sense says that they do. And then we come back to the question of equilibrium, which we talked about several days ago. The object is in equilibrium because the forces cancel each other out, and because it's not moving, we say that it's static equilibrium. And that's about all there is to say. So this is our first example of a free body diagram. I didn't give you a place to draw this, but let's just talk about it. Let's consider the same example But let's change it by saying, what if two people push the book in opposite directions? So let's say that Adam pushes the book to the left with a small force. So we would call that an applied force by Adam. And it would be aiming to the left, and it's drawn with a short arrow. And then let's say that Bill pushes on the book to the right with a bigger force. So again, it's an applied force, but this time it's Bill on the book. So what's the deal here? Well, the forces do not cancel, and you're left with a net force. So coming to our questions, how many forces act on this object? Well, 2. Do they cancel each other out? No. Well, are they in equilibrium, or is the book in equilibrium? No, so we can't say anything about that. But we can draw the net force in a different color on the picture. And I didn't give you any numbers, but I think you can imagine that if you've got two forces that are going in the opposite directions, the net force is going to be the force that goes in the direction of the stronger one, and it'll be equal to the difference. So for example, if Bill pushes with 15 newtons to the right, and Adam pushes with 5 newtons to the left, the net force is going to be the difference between those. It will be 10 newtons to the right, and that would be the arrow that I would have here. It's not exactly to scale, but it's close. Okay, so sometimes objects accelerate, right? This book would actually accelerate to the right, and we know that because we have a net force, and we kind of figured that out from our picture, or at least we're showing it from the picture. Okay, so free body diagrams, that's how they work. Okay, so with the class time that you have remaining, and I'd like you to work on doing some reading and some practice, and this is going to be your homework tonight as well. So go ahead and turn to the last page of your packets, the free body diagram packets. And you'll find these instructions at the end. Let's just read them together. It says, in your notes, sketch free body diagrams for the various situations described below. Check your work by looking at the key for the practice problems in the physicsclassroom.com website. The tutorial is called Newton's Laws, and the lessons are lessons 2C and 2D. So if you might want to even start by opening up your Chromebooks and going to those lessons. And the lessons kind of talk you through some examples, and they explain free body diagrams in a little more detail than I did. But then you can go ahead and you can actually start sketching out these examples. Do it in your notes. You don't have to draw any great artwork, but just go ahead and draw the picture and then diagram the forces that act on the book and label things appropriately. The nice thing about this is you can check your answers in the Physics Classroom website because the answers are all at the bottom. So it's good practice, okay, and you can go through and do these. So tonight what I'd like you to do is I'd like you to sketch out these situations in your notes, check your answers on the Physics Classroom. Notice that also on the last page there are a few more examples, and I'd like you to do those too. Tomorrow when you come back, what we'll do is we'll talk about this, and we're actually going to do a little activity where I'm going to show you some different situations, and you can walk around and you can sketch them out, and we'll talk about what's going on there. Okay, so have fun with free body diagrams, and I'll see you tomorrow.